All right, let's get right into this because this idea, it sounds completely backwards, right? We're about to explore one of the most advanced pieces of technology on Earth, the machine that makes the chips inside literally everything you own. And the craziest part? Its success hinges on being unbelievably, purposefully wasteful. And this phrase right here, it just perfectly captures the paradox at the heart of it all. To draw the microscopic circuits that power our modern world, engineers had to build a system that intentionally throws away almost all of its power. This isn't some flaw they're trying to fix. No, this is the whole point. So that's the big question we're going to unpack. Why on earth would you build a machine that runs on just 2% of its starting energy? Well, to get that answer, we have to go back to a fundamental problem in physics, one that, for a long time, seemed totally impossible to solve.
Okay, so here's the deal. If you want to draw smaller and smaller circuits, you need light with a shorter and shorter wavelength. So scientists went to what's called extreme ultraviolet, or EUV light. But when they tried to focus it with a normal lens, like you would with a magnifying glass, they hit a wall. A literal physical wall.
And you can see the problem right here. On the left, normal visible light sails right through the lens, no problem. It focuses just like you'd expect. But on the right, that same piece of glass becomes a brick wall for EUV light. It doesn't just block it. The light is so incredibly energetic that it gets instantly absorbed, basically tearing the material apart from the inside. Now let's look at the numbers, because they really show you just how big this challenge was. Visible light carries, what, maybe 3 electron volts of energy? But EUV light, it's not just a little more powerful. It's an absolute monster, packing almost 92 electron volts. That's a huge difference. And here's the key. Glass has something called a band gap of 9 electron volts. You can think of it like an energy shield. So visible light with its tiny bit of energy just bounces off that 9 EV shield. It can't break through, which is exactly why glass is transparent to our eyes. But EUV light, it comes in and hits that shield with 10 times the force needed to shatter it. It doesn't just pass through, it slams into the atoms, rips electrons away, and all of its energy gets absorbed instantly. In fact, EUV is so powerful it gets absorbed by pretty much everything, even the air itself. So it really looked like a dead end. I mean, if you can't focus light through a lens, what are you supposed to do? This is where the engineers had this absolutely brilliant, game-changing idea. It's one of those pivots in thinking that changes everything. They just took a step back and looked at the core problem. If every single material absorbs this light, if you can't possibly send it through anything, then you have to bounce it. You have to forget about lenses completely and build your entire system around mirrors. And that was the huge shift. So, out with the see-through lenses and in with this incredibly complicated system of mirrors, all operating inside a perfect vacuum because, remember, even air would stop the light. But look, we are not talking about your bathroom mirror here. Not even in the same universe. Each one of these mirrors is a masterpiece of science. It's made of 40 to 50 alternating super thin layers of 2 materials, molybdenum and silicone. And each layer is just a few atoms thick. These are literally the flattest surfaces humans have ever created. So how does this little atomic sandwich actually reflect something that's supposed to be unreflectable? Well, this is the magic trick. See, any one layer on its own can't do much at all. But by spacing these dozens of layers with absolute atomic precision, something amazing happens. The super weak reflection from one layer lines up perfectly with the reflections from all the other layers. It's a physics principle called constructive interference. All those tiny little light waves add up, they amplify each other, and they combine into one strong, focused beam. It is an incredible piece of engineering, but it comes at a very steep price. And this, right here, brings us full circle, back to our original question. We've just seen the incredible solution, these amazing mirrors, but this is also where all that so-called waste comes from. Because even with all that mind-bending nanoengineering, the absolute best reflectivity these mirrors can manage is about 70%. That means for every single bounce, 30% of the light's energy just vanishes. It gets absorbed by the mirror. So the key thing to realize is that this loss compounds. It stacks up. The EUV light has to bounce off about 10 of these mirrors to get where it's going. So let's just do the math real quick. You start at 100% power. After one mirror, you're at 70%. After the second, you're down to just 49%. By the time that light has made all 10 bounces,
You're left with a tiny little sliver, just 2.8% of the original power. That is where our 98% loss comes from.
But hold on, that brings up another question, doesn't it? All that lost energy, 98% of an immensely powerful beam of light, it has to go somewhere, right?
It becomes heat. An absolutely colossal amount of heat that constantly threatens to destroy the very mirrors it's hitting. If a mirror warps or expands by even a single nanometer, the width of a few atoms, the focus is completely lost and the chip is ruined. So on top of everything else, there's another layer of unbelievable engineering just for the cooling system to keep these mirrors perfectly stable. So after all that, after bending the laws of physics, inventing mirrors on an atomic scale, and then solving a crazy heat problem, why is it worth it? Why go through all that just to throw away 98% of your energy?
Well, this is why. This is the payoff. The goal was never, ever about being energy efficient. The goal was always about one thing: perfect, unshakable focus. All of that struggle, all of that waste, it's the price you have to pay to get from that blurry, useless mess on the left to the impossibly sharp, atomic-level perfection on the right.
And that's really the whole story. That 98% isn't a bug. It's not a flaw. It's the necessary sacrifice you have to make for precision. It's the cost of forcing physics to do what you want, so you can draw patterns so small you can only measure them in atoms. And that is how you solve an impossible problem, to create the technology that literally defines our world, powering everything from your phone to the entire future of AI.